Hello and welcome back to PC Retro Tech. In this week's video we're going to be looking at the king of IBM graphics standards, XGA. Now for most people that term came to mean a graphics resolution, 1024 by 768, but much more than that it is. Released in October 1990 by IBM, it was a whole new graphics standard and a very advanced one at that. You might remember in '87 they'd released three graphics standards for their PS2 line of computers, MCGA, the more advanced VGA that we're very familiar with, and an even more advanced graphics standard with a coprocessor, 8514/A. And it's the third of these that XGA is a successor to, and that makes it the most interesting of the IBM standards, along with its successor XGA2. Now, unfortunately for IBM, it was a commercial flop and so little known today that it doesn't even have its own Wikipedia page. Can you believe it? So we're going to fill in some of the missing details and even try and program a card based on the XGA standard in today's video. And you might have also noticed a couple of certificates on the wall behind me. These are finally the certificates for the Meteoric Awards, which the demo group that I was involved with won this year. We won in the Outstanding Technical Achievement category and got the Honourable Mention in the Best Old School Production category. There was also a little trophy, and we gave that to Viola, who was the graphic artist for the group, and he did such a huge amount of work on this demo. But it's really nice to have a couple of certificates to cover up a couple of holes that you would have seen in the wall here that were pretty ugly in previous shots on the channel. Anyway, enough of that, let's get stuck into XGA. This is my XGA card, a graphite card from Hercules, and most people who have one just think it's VGA. It has an IIT chip, Integrated Information Technology, a smaller graphics chip manufacturer you've probably not heard of unless you remember their maths coprocessors from back in the day. Apparently the company's still around, but it's called 8x8 now and does voice over IP or something. The chip is 1992, the year that IBM bought out XGA2, but as far as I know, this chip just does XGA. And IIT licensed the technology from IBM, along with bigger companies like SGS Thompson and Intel, and some other smaller companies as well. Now, we've seen this card on the channel before, but I was so confused by it, I put it aside and said I'd come back to it. I thought XGA, being IBM's successor to 8514/A, should be hardware compatible, but it was never intended to be. IBM only defined 8514/A at a software level called the adapter interface, a kind of driver if you like, and cards only needed to provide a driver to support that interface, even if their hardware was completely different. In fact, that was the case for XGA itself, and there was probably even a driver for 8514/A for this card. Now that we know that, hopefully we can get a bit further with it. Now I'd like to show you an original IBM XGA chip and card, but they're so rare and expensive. If you've got one, you probably sleep with it chained to your wrist in a steel case. And this card wasn't cheap either, but at least at the time, for me, it was quasi-affordable. If we're going to do anything interesting, we're going to need good information, and unfortunately this is the only data sheet for the chip itself. It covers their AGX 14 and 15. There is a 16 in the wild, but because it's not covered here, I know literally nothing about it. The 14 was for the ISA bus, and that's what I have, of course, that had a 16-bit engine. The 15 was for a local bus. For example, on a 486 you might have a Visa local bus slot, and this was a way for the chip to communicate directly with the CPU and memory subsystem at a full 32 bits. Now what I don't know is whether it could do bus mastering. Certainly on the PS2, XGA cards from IBM had a bus mastering option, and this enabled it to take over the bus and actually access all of the memory on the entire system. I don't know whether that was possible here. I certainly know bus mastering was not supported on the ISA version. Now this was an XGA implementation, and I don't know whether you noticed this, but AGX is XGA backwards. It supported a bunch of previous standards as well, which is quite nice. And there were three memory options, 1, 2 and 6 megabytes. Now they mention a resolution of 1280 by 1024 and 24 bits here in both cases, which is a bit odd, but I think what they're saying is in the 1 megabyte case, you could go up to the maximum resolution or color depth, but not at the same time. There was a trade-off. You'd need a 6 meg card if you wanted everything, and that makes sense. A little over 1 million pixels at 3 bytes each would be more than 3 megabytes. Why 6 megabytes, you might ask? Well, with XGA, it was standard to have some stuff drawn in off-screen regions of video RAM and then blit them into the visible portion. So you always had more video RAM than you needed for the display. And in any event, you could always cut down the resolution a little bit and get multiple pages. Now, some of these features here don't make any sense to me. From what I've read elsewhere, this was just standard XGA, not very much more, and very few features missing. It wasn't 100% XGA compatible, but close. And certainly polygon clipping, complex polygon pattern fills were XGA features, and I imagine you could describe a pattern fill as color dithering. But what is object shading and surface mapping? They sound like 3D features, and this is definitely not a 3D card. Marketing speak maybe? Or perhaps those are names of Windows Accelerator features that just happen to be supported by XGA. And they timed their card against a bunch of carefully chosen competitors, including the super fast ATI and a standard Super VGA, whatever that is. This was done on a 486DX33 in the XJ mode, 1024 by 768, and of course they came out on top. Now, the chip itself had a Super VGA core. This was the Super VGA era, after all. And it also had a coprocessor. This is the descendant of the 8514/A coprocessor. It was 300 million instructions per second, and I believe it was rated for 40 megahertz. And this supported color depths of 1, 2, 4, 8, 16, and 24 bits. And that's interesting because XGA didn't have 24, and the 16 wasn't supported by the coprocessor. So this 24-bit mode is so-called true color mode, something the clone card manufacturers were marketing. It had 8 bits of color in each color channel. So it does look like this card is going to do something that XGA didn't. This is a Visa local bus setup, and you can see the chip talking directly with the portion of the slot for the Visa local bus, and the ISA is connected to the rest. But very generic information here. There's nothing about any of the registers in the chip or any way to program this. And you can see that I just mentioned dithering, object shading, surface mapping again, no explanation. There's even a little typo here, I think. 64 million colors in the 1 megabyte version and only 16 million colors in the 6 megabyte version. So yeah, we're going to need better information than this. We're going to get a lot better information from this book here, Programmer's Guide to the EGA, VGA and Super VGA Cards by Richard Ferrero. This is a huge book, and it contains an absolutely massive collection of information about how to program all manner of graphics cards, including a lot of Super VGA accelerators, and there's a lot of information that will be very hard to come by any other way. This book contains an entire chapter on the IIT chips, but don't get excited just yet. They mention that the IIT chips are Super VGA controllers, although they do say that the AGX 14 and 15 are XGA clones, and that they're functionally identical, apart from the ISA local bus distinction that we already know about, and that if you want to program these things, just treat them like ordinary XGA chips. And in fact, there's an entire chapter in this book on programming the XGA at the register level. Unfortunately, I can't recommend it. This book is quite well known, and deservedly so, for the wealth of information that they include, much of which would be impossible to find nowadays. But in that particular chapter, they make a decision on what might be interesting for the reader and just leave everything else out. And that includes information that's critical to XGA, such as how the mask map works, for example. And then when it comes to setting up video modes, they say, well, that's beyond the scope of this book, and we couldn't possibly include all that information. despite the fact there's just 2 pages of numbers that they would have had to give. So along with some errors in the presentation that make it a bit hard to follow, I just can't recommend that particular chapter. There are better resources, fortunately for us. Wouldn't it be interesting, though, to contact this guy, Greg Tupper, who supplied all the original technical information about the IIT chips? I wonder if he still has that all these years later, if he's still around and active. And apparently Orchard Technologies provided them with an actual card. I presume they mean AGX 15 here. But in terms of the information here, there's not very much. They just list the AGX specific registers and their indices. Very, very brief description of how to program them. Really not enough information. There's a section on the hardware cursor, which I'm not really interested in, and how to identify the chips. But that's about it. This is the end of it here. And the most interesting thing actually is this chart of video modes. You can see there's some 800, 600 modes which are not XGA standard. And there's also this 24-bit per pixel mode, so-called true color, which XGA didn't have. They did add that in XGA too, but I don't know whether it was supported by the coprocessor or not. Even the 16-bit modes were not supported by the coprocessor on XGA. But here you can see the only mode that's not a coprocessor mode on this chip is this one here. So it does look like there's some differences with XGA. Now there is one other book I want to show you, but before I get to that, I just found this document here. It's a text file on the IIT AGX series, and it actually contains some really interesting information. It mentions an AGX 10 and 11, which I wasn't aware of, and apparently that was the original AGX chipset. And it says that the AGX 16 was the one that gave PCI support, so I didn't know that. And I guess it makes sense in retrospect, and apparently it had more clocks, whatever that means. It says the AGX chips are basically XJ with a Trident VGA part tacked on. And the rest of the document is very terse. It just lists the registers and what the individual bits do, but there's no real information on how to program the thing. At the bottom is a list of video modes, and I presume these are BIOS modes, although I didn't actually check that. And of course it includes the XJ mode, 1024 by 768. No mention of a 1280 by 1024 mode, which is quite interesting. And some of the registers are only for the AGX 10 and 11 or the AGX 16, which won't be relevant to us. So in total, there's really not a lot of information in this document for us. Fortunately for us, there's one more reasonable option for XGA programming. This one here, the PC Graphics Handbook. And this one actually has a lot of low-level register programming information for XGA, and it doesn't seem to leave out any of the really important information that you need. Now, we're not going to find any information about our chip specifically in this book, but at least it has information about how to program the XGA, including this table here with all the numbers that you need to get into the various video modes that XGA provided. So there's the XGA resolution, 1024x768, and IBM had a 256 color version and a 16 color version. And then there was a lower resolution mode, 640x480, with 256 colors. And then this mode here, which is a little bit different. So this is what they call the direct color mode. And the way it worked is that instead of the colors being an index into a lookup table, where the actual color information was, the so-called palette, this mode had the color information directly in video RAM. And if I remember correctly, they broke the 16 bits up into 5 bits, 6 bits, and 5 bits for the red, green, and blue channels. And so that information was just taken directly from video RAM and sent straight out to the digital to analog converter. But there's a disadvantage with this mode. You can't use it with the coprocessor, so you can't do any of the drawing functions in 16-bit color. So that's really a shame. It would be nice to have 65,536 colors and a coprocessor. But fortunately, if the tables in that other book are correct, our chip actually does that. And not only that, but also a 24-bit color mode, which is really incredible. And I guess I'm only going to get a very low resolution with the amount of video RAM that I have, but at least we should be able to try that out and see if it works. Now you might be wondering how the XGA works at this point, and actually it's very similar to the 8514/A. So I'm going to describe them both up to the point where they're actually different, and I'll let you know when we get to that. So first of all, they can both draw polygons and fill them in. And so supposing you've done that and you've done it in an off-screen region and you want to put it into a visible portion of video RAM. So the traditional way of doing that is just to copy the bytes over one by one to copy this rectangle into the destination region. Now that's going to be pretty slow because it'll tie up the CPU, and so it's nice to have a separate device that can do this for you. A so-called Bitblock Transfer device, or a Blitter for short. And basically it can copy a rectangular region over while the CPU is doing something else, and so that's going to save you a hell of a lot of time. So the coprocessor for these adapters has a Blitter, and in the 8514/A it can copy data from a rectangle in the system memory into video RAM, or it could copy from video RAM to video RAM, or actually go back the other way from video RAM back to system RAM. And XGA has all of this as well, but it basically can copy from anywhere to anywhere, or at least the original XGA could. So it could even go from system RAM to system RAM. But just copying a rectangle is a bit inflexible because it's just going to overwrite whatever's in the destination. But that's not going to be very convenient if you've already been building a scene up on screen and all you want to do now is copy the next polygon over and overlay it on top of the existing scene. And so they needed to make things a little bit more flexible, and one way they did that is with a write mask. So this works by color channel, and you can mask off certain color channels. For example, I could mask off the blue channel here so that it can't be modified, and then copy the data across, and then I'll get a red triangle overlaid over the blue one. Of course, you're going to get purple pixels where the two triangles overlap because you've still got blue channel information there, which is not modified, and you've copied red channel information in, and red and blue combine to give purple. Now that might not be what you want, and so you need a little bit more flexibility still. And another way they did that is to provide a compare function. So this allows you to only modify the destination pixel if the new pixel color is greater than the existing pixel color, or you could set it up so that it only modifies if it's less than the existing pixel color. Now that'll actually work quite well for a situation like this where we just have two triangles and we just want to overlay one on top of the other. But if those triangles were filled with a pattern, or if we had a more complicated scene where we had lots of different objects, the only way you can do it like this is color by color, in color order from the lowest color value to the highest, or vice versa. And I'm sure you can see that's going to get really complicated really quickly. So we need something a little bit more flexible than this. So the next feature that IBM added to these adapters is something called a mix. And this allows you to mix color information from the source rectangle and the existing pixels in the destination rectangle. And you can apply a bunch of different functions. In fact, there's about 16 different ones that you can use. For example, you could just add the color values together, or you could subtract them, or you could use a logical operation like XOR, or a logical AND, or logical OR, and so on. And each of these will give a different kind of effect. XOR is really useful, for example, if you want to temporarily put something on the screen and then take it away again later, for example, if it moves. It turns out that mathematically, if you do an XOR with some information and then XOR it with the same information again, you go back to the original image. So that's a really useful one. And there's all different ways that you can use these functions for all kinds of different effects. For even greater flexibility, IBM offered additional mixes. For example, in the 8514/A, there were already two mixes called the background mix and the foreground mix. And I'll explain how these were used in a moment, but these could be arbitrary functions of the source and destination pixels. Any one of those 16 functions could be used in either case. And there was nothing stopping you using just the source pixels for one of the mixes, for example, and if you wanted, just the destination pixels for the second mix. And so what we need now is some way of deciding which pixels are going to get copied into the destination. And you can actually do that on a pixel by pixel basis, selecting from either mix 1 or mix 2, using something called a pattern. On both of these adapters, the pattern had to be a monochrome image, black and white, and it allowed you to specify pixel by pixel whether color information would be taken from the first mix or the second mix and copied over to the destination. So if there was a black pixel in the pattern, then the color information would be copied over from the first mix, and if there was a white pixel in the pattern, the color information would be copied over from the second mix. So this really allowed you to cut out shapes from one of the mixes and take all the rest of the pixels from the other mix. And actually the pattern really didn't have to correspond to either mix, it could be arbitrary. But there were some limitations. On the 8514/A, there were only certain places the pattern information could come from. One possibility was to take it from system RAM, in other words, you'd supply the pattern yourself, and it could be arbitrary, anything you wanted. Another possibility was to use a repeating pattern of just a couple of bytes. You'd put those into some special registers in the coprocessor, and then they would just be repeated over and over again for the pattern information. Now that'd be useful if you wanted to fade one image into another image. Basically you just add more and more black pixels to your pattern information, and it would just take more and more pixels from the first mix instead of the second mix. Now the other place that a pattern could be taken from is the source image itself, and this was a little bit more involved. Basically you could set up a mask which would ignore certain color channels, and the other color channels would then be combined together. If any of them were set, then the pixel in the pattern would be set. And this was done on the fly using the Blitter. Now XGA was a little bit different. So what it did is it had 3 maps. So they're basically just rectangular blocks in memory somewhere. They could be in system RAM or they could be in video RAM. It didn't really matter. It was arbitrary. And for example, you could set up some mixes based on these maps. The other thing you could do is set up a pattern based on one of these maps. Of course, that would have to be a monochrome image, but it also had the ability to convert color images from one of those maps into a monochrome image. And then basically it would work exactly like the 8514/A, but without the Blitter limitations. But in addition to that, IBM added another feature to the XGA that the 8514/A doesn't have. That new feature is something called a mask map. It's another monochrome image which can be anywhere in memory, either video RAM or system RAM, and it allows you to specify pixel by pixel which parts of the destination image are allowed to be modified. So to recap what we've got so far, we've got 16 different functions that we can use to mix pixels from source and destination, and that can be used to give us 2 different mixes using any of the 16 functions for each. We can then choose pixel by pixel which of the 2 mixes we want to take colors from, and that will give us some kind of image, but then we can filter that image pixel by pixel to decide which of those are going to be allowed to modify the destination. So this is a really powerful pipeline, and the amazing thing about XGA is that every operation in this pipeline can be done all at once. So that makes it really fast, no more using multiple blits to get stuff done. So after all of this stuff has been done, we might end up with a destination image that looks like that, and I'm sure you can see the endless possibilities that you could have with a system like this. But the important thing for IBM was that all of the steps up to here are basically the same as for 8514/A, just with some minor modifications. And this meant that they could have the same adapter interface available for 8514/A and for XGA. So you'll often find drivers for the adapter interface for all sorts of cards, including XGA ones. Before we get onto the XGA card, I want to give an update on my ATI 8514/A clone card, which I showed in a previous video. I had this program which draws a triangle on the screen, fills it in, and then uses the Blitter to copy it across the other side of the screen. But I couldn't get the Blitter to work properly in IBM mode. Basically, it was just giving me black rectangles or filled rectangles, and what I wanted is for it to look at the pixel color in the source image and use that to decide whether to copy the pixel across or not. So it wasn't working previously, and I now have it going, and it turns out there were two issues that were causing problems, and the first has to do with a color mask that's applied to the source image. The color mask masks off certain color channels, and whatever's left is used to decide whether to copy the pixel across. It's just a decision value 0 or 1. And unfortunately, IBM in their infinite wisdom rotates the color mask that you supply right by 1 bit before applying it. Now, I knew about this, and I'd actually taken that into account in a few versions of my program. But another issue that I hadn't taken into account is that the decision value that results, that 0 or 1, gets put into bit 7 of the color that gets copied over. Really utterly bizarre. And unfortunately, I didn't have any colors in my palette other than the first 16. All the rest was set to black. So when that bit 7 gets set, 2 to the power of 7 is 128, it effectively adds 128 to the color value. And so what was happening is it was basically just doing a whole load of black pixels because I just had black in my color palette. So the solution was pretty easy. All I had to do was duplicate the lower half of the palette in the upper half and basically make sure there's a full 128 colors there. So that means that whenever a color is specified and bit 7 gets set, it'll just give exactly the same color in the upper half of the palette, and then everything works fine. So finally at last we have the ATI Blitter working in ordinary IBM mode. The first thing I decided to try with this XGA card is the actual video modes that were on the list I found in that text file. And they don't quite match up, but they're pretty close. So this is supposed to be 800, 600, 16 color, and for some reason I get black and white. This is mode 5B. 5C is supposed to be 640, 400, but it doesn't work on any of my monitors. There is something there, it's just not picked up by the monitor. And 5D also doesn't work on this monitor, but it does on the LCD. It's a 640, 480, 256 color mode. I have no idea why it doesn't work on the NEC multisync. 5E is the next one, and this is an 800 by 600 256 color mode. And then 5F is what looks like an interlace mode. It's got a lot of flicker, black and white, 1024/768. Again, it's supposed to be 16 colors. It's a big jump then to 64 hexadecimal, and this is the XJ mode, 1024/768 at 256 colors, and the next mode, 65, is the same, but it just shifts it a little bit on my monitor. It's interesting that this first graphics mode listed, 54 hexadecimal, doesn't seem to work on this card. I tried it on a couple of different monitors and there's just nothing there. I don't know whether that's to do with the version of the chip, or maybe they just left it out of the BIOS on this graphite card. We also haven't got any 16 or 24-bit per pixel modes here. The BIOS only supports 256 colors or black and white, although apparently that's supposed to be 16 colors. And we have to step away from getting into video modes using a BIOS interrupt if we want to do anything more. If you're prepared to use the registers, AGX mode register 10 for example, has a bit for selecting 16-bit per pixel mode. And we're definitely going to have to try that out, especially if we can get the coprocessor to work. I'm betting no one has used the coprocessor for anything interesting in 16 or 24-bit mode since the chip was designed. And the reason I say that is, although Windows would have supported for drawing boring rectangular windows, the only people actually using the coprocessor for drawing objects would be CAD people. And I'm betting that the CAD software wasn't rewritten to support all these non-standard, non-IBM modes. So we may be the first people to actually use it for something interesting. The other thing I found interesting about this card is it's very Super VGA-like, and that's not surprising given that it has a Super VGA core, essentially a Trident core. And basically all of these modes have a lot of VRAM, usually a megabyte or more, especially in the high color modes. And the processor address space just wasn't big enough for that. I mean, the 8086 and 8088, for example, only had 1 megabyte of address space. So only 128K was actually allocated for video modes. And so that means that VRAM has to be banked. And so basically you can set it up to either use 128K banks or 64K banks. There's an old and a new method, and they differ. It's a little bit more convenient to use 64K banks because the segment is 64K on these processors. So this is how SVGA worked, and in the early days every card had a different way of doing this. A little bit later they introduced the Visa BIOS, which had some functions that would tell you which method was being used by the card, but before that it was just a nightmare. Fortunately, we only have one card to worry about here, and it's very simple. And in any case, we're really interested in getting the coprocessor going. Well, it may not look like much, but I have the coprocessor working. This line was drawn with a drawing function of the coprocessor. And I had a little bit of anxiety about this because in order to draw anything at all, you have to set up a destination pixel map. And the upper left corner of that is given as a 32-bit address. But how do I do that on a 16-bit system like DOS? Well, it turns out that the coprocessor accepts 32-bit addresses, even though the system is only 16-bit, and basically it interprets anything from 32 megabytes onward as accessing video RAM. So that's great because it means the coprocessor itself can access video RAM as one big block of memory instead of having to worry about all these 64K or 128K pages that SVGA has. To make the line drawing more interesting, I'm rotating a wireframe object, but it's flickering. That's because I'm drawing lines, blanking, drawing, blanking, and so on. One way to fix that would be to use double buffering. Draw the object in an off-screen buffer, and when it's done, switch the buffers. But to do that, I'd want to sync with the screen, and so I'd need to detect the vertical retrace of the CRT monitor. One way to do that is with the CGA status register, but unfortunately it's not supported by this mode. The standard way is to use an XGA vertical retrace interrupt. But according to that text file I found, it's not actually implemented by this chip, which is really annoying. Now, I didn't check if it's implemented as a VGA interrupt instead, and the IRQ2 line that would be required for that is actually connected to the ISA socket, so it's possible. But I realized that once we start filling these triangles, it's going to be too slow, and you'll see the fill unless it's all done off screen. So I'm going to need to blit the whole object onto the screen at the end anyway. And that's just going to make the problem go away automatically, so why try to solve it now? I seem to have run into a couple of problems. You're supposed to be able to set up a map that's any width and height to draw in. And I knew that the IIT had a limitation that the width had to be a power of 2 for performance reasons, but it seems that if I set it to anything other than the width of the screen, this happens. Here I set it to 1/4 of the width of the screen, so it goes across one line, and instead of resetting for the next line, it just keeps going, and so you'll end up with 4 lines next to each other, and of course this makes the whole image 1/4 of the height. So looking at the diagrams in the book, this is not how XGA is supposed to work. I don't think it'll be an issue in the long run. I'll just set the map the full width of the screen, and it is actually possible to do blitz from a region within a map to a region within another map. So that's all we really need to be able to do. It's just a shame that this is not working properly though. The other issue I had is the coprocessor was overheating. Basically, one of the chips was getting really hot, and the only thing that fixed it after lots of fiddling was sticking it in the fridge for half an hour. Well, I have made some progress, but I wish I could say it was easy. I have actually been having some problems with the card. It hasn't had the issue with the coprocessor overheating that I mentioned earlier, but about every third time that I restart the machine, it hangs like this. We also get a lot of corruption like this, and there's various variations on this, so there's obviously some issues with the hardware itself. But by far the biggest problem is documentation. I've been at this hours now, and it's still difficult to find options to put in the bits in the registers that actually work together properly. For example, I discovered that to do area fill, you have to have the source image in monochrome, or so it seems, like I had originally with 8514/A. And monochrome images are very small, they're just 1 bit per pixel. So that means that you can't see it anymore, or at least those flashing dots are the source image. And it's repeated 8 times because of the problem I mentioned earlier with the map width. In order to fix that, I'd have to have the map width 8 times bigger than the width of the screen, but you can't use a number that high. So the other problem should go away, that's the lines going through the image. That's because I'm using the wrong line drawing routine. There's a special one for area fill. So hopefully I can fix that. And also I have colour now. Basically the right mask was more or less disabled. Really useful. Anyway, the next thing will be to get rid of the lines and to hopefully have a more pleasing palette. I've made some progress. I moved the original monochrome image to an area of VRAM just below the bottom of the screen so you can't see it. And of course all the lines are gone now. That wasn't just the special line drawing option for area fill, but the lines also need to be XORed, and that's done by setting that option in the mix. It's still flickering a lot. That's because I have to blank the image after each time the object's drawn, and the only way to fix that will be to do a final blit after each time it's drawn to another location. Now of course it looks a lot worse for you guys because, as I've explained previously, this camera can only manage about 1/3 of the refresh rate of the monitor, but that'll also be fixed by the final blit. One problem I can't solve though is the colouring. According to that text document, this chip does not support the XGA palette registers, which is really annoying once again. I did try the BIOS functions for setting the DAC registers, and they just hang the machine. And I also looked around for information on how Trident does this, but I couldn't find anything. So that's a problem I'm not going to be able to solve, at least this week. But let's try and sort things out with this final blit. Well, after a marathon effort, here's the result, finally at last, on the right. I picked a string of colours in the existing palette that's kind of in order of intensity. It doesn't look as good as what we had on 8514/A, but yeah, it's a little bit better than it was previously. I did have a little bug actually. I was blanking far too often, and so that was contributing to the flicker. Should be completely smooth on the right hand side now though. If I switch turbo on, it'll go quite a bit faster, and I think these speeds are about what we had with 8514/A, so not breaking any records here. I'm using triangles exactly the same size, but they look smaller because of the higher resolution. I think it's just a little under 20 frames a second, something like that, on the slow mode, and maybe at double speed on the fast mode. So in all, not too bad, but yeah, a lot of issues along the way, that's for sure. Well, we seem to have reached about the same point as we did with 8514/A, but there's still so much more to cover. We didn't look at 16 or 24-bit colour yet, or the pattern and mask maps, which are really characteristic of XGA. But there's so much I have to sort out before then. Fortunately, I didn't have to put the card back in the fridge, which I was pleased about, but it is slowing me down a little bit that I have to restart it so often. And the documentation is really terrible. I found in the end a document from INMOS about their chip, but unfortunately it only gives about 1/4 of the information that would be required to program it, and it's the same with pretty much all the sources. And I have to wonder whether this documentation issue is partly what led to the downfall of the standard. IBM had documentation for the original XGA, but it was very tied to the PS2 and microchannel architecture, how to detect the card in that hardware, and all about their memory management and so on. And this was just irrelevant for everybody else, especially all the clone manufacturers. Why pay IBM for a license when you can just look at what the standard does and then just implement the features you like? And so a lot of Super VGA manufacturers did precisely that. There were blitters in lots of them, and they had very similar features. But they're all completely different, of course. There was no common standard that emerged there. You basically had to write specialized code for each of the different chips. So the whole thing ended up being a bit fractured in the end, and for IBM's part it just flopped completely. Instead of XJ being associated with a coprocessor as they surely hoped, it just ended up being in graphics mode for a lot of people. So it's a little bit of a shame, I think, that this very interesting standard ended up dying in the way that it did, but it still lives on in all of these other cards that we have in one way or another. Anyway, that's going to be it for this week. A very long video, I know, but there'll be another one a little bit later on when I finally sort out some of these issues. Thanks very much for watching, and we'll hope to see you in the next one. Bye!